Okay, well, welcome everyone to the Air Sea Fluxes from Space webinar series. Today we have Lucie Reymondet, who's a graduate student at Scripps, and she's going to be talking about Southern Ocean latent heat flux variability driven by oceanic meso and submesoscale motions. And I'll let you take it away, Lucie.
Thanks, Sarah. So hi everyone. As Sarah said, my name is Lucie. I'm a second year PhD student here at Scripps Institution of Oceanography, and I work with Leah Siegelman and Luc Lenain. And today I'd like to share some work that we recently submitted to Journal of Climate on Southern Ocean latent heat flux variability driven by ocean meso and submesoscale motions. So to start very generally about very generally about why we care about air-sea heat fluxes in the Southern Ocean at all. The Southern Ocean is a key region for oceanic uptake and storage of anthropogenic heat, regulating the global overturning circulation. And heat fluxes between the ocean and the atmosphere in this region can have far-reaching climate impacts. And relevant to this is a recent study by Kang et al. In 2025. This is a figure from their study that shows the observed cooling trend of sea surface temperature over recent decades. And most climate models, CMIP class models, fail to capture the observed cooling in the Southern Ocean Pacific sector and in the Southeast Tropical Pacific. And this is problematic because spatial patterns of SST in the Tropical Pacific play a central role in setting global climate through phenomena like ENSO. And using a kilometer scale coupled model, Kang et al. Were not only able to successfully reproduce this cooling trend, but also show that the cooling of the Southern Ocean actually drives the cooling in the Southeast Tropical Pacific. And they suggest that the reasons for this fidelity is twofold. First, that their model explicitly resolves heat transport by eddies in the Southern Ocean. And second, that it simulates realistically strong cloud feedbacks. So these results really highlight the importance of accounting for eddy scale heat transport processes, especially in the Southern Ocean, because they can play a role in these teleconnections from the extratropics to tropics. However, the Southern Ocean is sparsely observed owing to extreme environmental conditions and frequent cloud coverage. And this is particularly true in the austral winter, June, July, and August. And I like this figure from Swart et al., showing the number of observations in the Southern Ocean for austral summer. So December, January, February, over 10 years of observations, and then the equivalent in the austral winter, showing very sparse observations. And I do want to point out, however, that two moorings have provided a multi-year time series of in situ observations, and those are the Ocean Observatory's initiative mooring in the Southeast Pacific that was operational from 2015 to 2020, and the Southern Ocean Flux Station mooring south of Tasmania that has been intermittently operational since 2010. And these two moorings have been invaluable in understanding the temporal variability of air-sea fluxes locally. However, two moorings, let alone one today, cannot capture the spatial variability of air-sea heat fluxes across the Southern Ocean. And this variability is quite challenging to constrain, especially for turbulent heat fluxes, because they are inherently the result of both ocean and atmospheric variability. And so they cover a broad range of scales in space and times. And just to name a few, I'm going to illustrate these scales on a schematic by Seo et al. That is great because it really illustrates this variability in space. And so this pictures an atmospheric storm, a low pressure system denoted by an L, traversing a semi-permanent SST front. Here it's labeled as a Western Boundary Current, WBC, but it could be equivalently the Antarctic Circumpolar Current. And what happens here is behind the cold atmospheric front, so in blue here, when the cold atmospheric front crosses the SST front, this creates large air-sea temperature differences, triggering high heat flux locally, and a similar process might occur over warm mesoscale eddies, causing high upward turbulent heat fluxes there too. I'm going to pause just here and say that throughout this presentation, we're going to adopt the convention, the sign convention, that positive turbulent heat fluxes are ocean heat release or ocean cooling, so upward. And so in contrast, going back to the schematic, behind the warm atmospheric front, the red line here, warm air overlies relatively colder water, and there we would have lower heat flux. So I really like this schematic because it illustrates the scales that I'm going to be referring to throughout this talk. Those are the atmospheric synoptic scale. So that's the high and low pressure systems that typically have widths of on the order of thousands of kilometers and lifespans on the order of 2 to a few days. It also illustrates atmospheric high frequencies corresponding to cold and warm atmospheric fronts. These are typically less than 200 kilometers wide, and they pass very swiftly over any point in space within a few hours, less than a day for sure. And finally, it also illustrates the ocean scale, so large scale fronts like western boundary currents and the Antarctic circumpolar current, but also mesoscale eddies on the order of tens to hundreds of kilometers wide, and submesoscale fronts on the order of 1 to a couple of tens of kilometers wide. And these features, mesoscale eddies, submesoscale fronts, typically persist anywhere between a few days to weeks, maybe a month or so. And so there is observational evidence of the influence of these sources of variability, both atmospheric and oceanic, on turbulent heat fluxes in the Southern Ocean. And we choose to focus on latent heat fluxes. I'll get to that just a little later. But so evidence of this influence, oceanic and atmospheric, on turbulent heat fluxes in the Southern Ocean are first concerning mesoscale eddies, so on the order of tens to hundreds of kilometers. These have been shown to enhance turbulent heat fluxes locally, promoting vertical mixing in the atmospheric boundary layer and thereby increasing near-surface winds. And this mechanism was revealed by Frenger et al., for example, using satellite observations of sea surface temperature and near-surface winds in the Southern Ocean. And the figure to the right here shows their satellite-based composites of SST and wind, normalized by eddy radius. Those are the black concentric circles. And what this shows is that positive mesoscale SST anomalies trigger positive mesoscale wind anomalies through the air-sea flux mechanism described to the left. And this effect is reversed for cold eddies in the Frenger et al. Study. Another source of variability, atmospheric this time, is polar air outbreaks. And these are associated with extreme ocean heat loss events. This was evidenced, for example, by Ogle et al. In a study where they used data from the Ocean Observatory's mooring that I mentioned earlier in the Southeast Pacific. And the map to the bottom illustrates a polar air outbreak with a low pressure system bringing in relatively colder air from the Antarctic continent over the mooring and winds blowing to the northeast. And the scatter plot in the upper part shows that these northeastward winds are typically associated with the most extreme daily mean turbulent heat flux values. And I will just note here that the sign convention was flipped in the study by Ogle et al. But these are ocean heat loss events, extreme ocean heat loss events. So these are just three, I guess, examples of sources of oceanic and atmospheric variability that impact turbulent heat flux variability. But really, turbulent heat fluxes variability covers a broad range of spatial and temporal scales, and these are complex to simultaneously observe and model. So for this work, we chose to focus on latent heat fluxes because they, by definition, they transfer not only heat, but also moisture from the ocean to the atmosphere. And thereby they play a role directly in heat and water cycles in the region. So that made them of particular interest to us. And also, typically, they were observed to exceed sensible heat fluxes over warm SST anomalies in magnitude. And so we chose to focus on latent heat fluxes. Now, the mechanisms by which the ocean mesoscale and the atmosphere influence latent heat variability are well understood. However, we identified a few knowledge gaps, and they are the following. So first, we found that quantitatively, we don't know the relative oceanic and atmospheric contribution to latent heat flux variability down to kilometric spatial scales and hourly temporal scales. And this research is timely because Sarah, you were mentioning the Simmer mission right before we started, but also global long runs of coupled models at kilometer scale are starting to emerge that enable us to investigate these questions, like the study by Kang et al. Demonstrated. And second, at the smaller scale, the local atmospheric response to kilometer scale SST fronts in the Southern Ocean is poorly characterized. Submesoscale SST fronts were shown to induce distinct atmospheric response in other ocean basins in recent model studies in the Kuroshio and in the Gulf Stream, but none have addressed the Southern Ocean. And so the questions that we asked here are the following. First of all, what is the relative contribution of the ocean and the atmosphere to latent heat flux variability in the Southern Ocean, in the case of this study? Second, what are the characteristics of the atmospheric response induced by ocean submesoscale fronts in particular in the Southern Ocean? And finally, can ERA 5 capture these processes? And to answer these questions, we used a global coupled model that was run at NASA, the Coupled Ocean Atmosphere Simulation, or COAS. And in this model, the ocean is modeled with MIT GCM and a horizontal grid spacing of 2 to 4 kilometers. The atmosphere is modeled by the Goddard Earth Observing System with a horizontal grid spacing of 6 to 7 kilometers. And the simulation spans roughly 15 months with hourly outputs. And I'm going to animate the map to the left, which represents sea surface temperature, heat map and contours overlaid with 10-meter wind vectors in a portion of the Southern Ocean that's southeast of South Africa, and you can see the Kerguelen Islands represented to the far right here. So I think COAS is a really beautiful and fun data set to work with because it captures down to fine spatial and temporal scales the ocean and atmosphere variability simultaneously. In the Southern Ocean, winds predominantly blow from the west, but as you can see from the animation, but now and then synoptic pressure systems will pass through the domain over a few days, and they are bordered by swift atmospheric fronts that you can recognize in the animation, maybe from the drastic and very quick change in wind direction, but also in the background, slowly evolving is the SST field with meanders and mesoscale eddies bordered by sharp submesoscale fronts. And if you think this is beautiful, like I do, I think what is even better is when you look when you replace the heat map by latent heat fluxes instead of SST. And this is the picture that you get. So here, SST contours are still in the background, and the vectors still represent 10-meter winds, but now the heat map represents latent heat flux out of the ocean. And so what we see when I animate this hourly animation is that latent heat fluxes bear the fingerprint of oceanic variability of those meanders in the background and those eddies. And you can see that the heat map for latent heat fluxes is really locked into the spatial pattern of the meandering and eddying SST field, so to speak. But latent heat fluxes are also modulated by atmospheric perturbations that pass through. For example, when a storm passes through, latent heat fluxes are suppressed ahead of the storm in the warm sector. That's where they're either white or bluish in the animation. And they're very much enhanced in the lee of the storm where that lights up in red in the cold sector. And this animation really brings to life the scales that were described just earlier in the schematic by Seo et al., showing both the large and rapidly changing atmospheric scales, synoptic scale and high frequencies, as well as the smaller but also slower evolving ocean mesoscale and some mesoscales. So truly, I think COAS is a great tool to explore these coupled processes down to kilometer and hourly scales. But we're going to take a step back first and look at the Southern Ocean big picture in a statistical sense to get a lay of the land or lay of the ocean, I guess. And I'm going to start with this map to the left that represents the annual mean latent heat flux in COAS. And the gray zone around Antarctica represents the seasonal sea ice extent. Off the bat, I'm going to define two regions that we'll come back to later that are represented by boxes here. One in the Agulhas retroflexion and return current south of South Africa called Agul, and one off the tip of Chile in the Southeast Pacific called Chile. What this map shows is a heterogeneous picture with hotspots in the latent heat flux mean, notably in the Brazil-Malvinas confluence, in the Agulhas retroflexion and return current, and, for example, on the edge of the Kerguelen Plateau. And to give kind of a sense of what these hotspots represent, the average latent heat flux mean in the Agulhas region is 2.5 to 3 times, 2.5 times what it is in the Chile region. Now, looking at the variability of latent heat fluxes around this mean is this map. So this represents the standard deviation, annual standard deviation of latent heat fluxes in COAS. And here again, hotspots emerge in the variability that visually correspond with hotspots in the mean. And here again, the ratio between the Agulhas region and the Chile region is quite significant, with a variability in the Agulhas region that on average is 2.5 times greater than in the Southeast Pacific region. And finally, this last map shows the SST variability through the SST gradient standard deviation. This really tells us how much in a given location eddies and fronts move or change through time. And here too, visually, there's a correspondence with the maps to the left with hotspots of SST gradient variability. So this is an annual statistical view, and to kind of get a feel for what's going on here, we're going to take a closer look at what happens in each of these two regions, in the Agulhas, Agul, and in the Southeast Pacific, Chile. And we're going to start with the Southeast Pacific. So this is an animation like we saw earlier, a latent heat flux heat map with SST contours and 10-meter wind vectors in the Southeast Pacific. And what this shows is that in this region, latent heat fluxes are mainly modulated by atmospheric synoptic pressure systems that pass through the domain. And that SST, visualized here through contours, doesn't seem to control or influence latent heat flux distribution much. So a weak SST imprint. Sometimes atmospheric fronts come through and separate regions of positive and negative latent heat flux. And this is a textbook example of a storm-induced latent heat flux pattern, positive in the cold sector and negative in the warm sector. Now, in the Agulhas retroflexion, the picture is quite different. Here, latent heat fluxes are strongly modulated by the ocean mesoscale eddies and some mesoscale fronts in the background. And wind variability, however, is qualitatively comparable to Chile, to the Chile region. Sometimes the entire region lights up in red, signifying that atmospheric variability at that point in time dominates. So overall, latent heat flux is strongly modulated by ocean mesoscale eddies and submesoscale fronts. And moving on from here, we will consider the Agulhas retroflexion region to be a strong ocean atmosphere coupling case and the Chile region to be a weak ocean atmosphere coupling case. Now, sorry. Both these regions are approximately 1,000 by 1,000 kilometers, and we compile 11 months of latent heat flux fields on which we perform wave number frequency spectral analysis. And this gives us wave number frequency spectra. And we're going to start with Chile again. So this here is the annual latent heat flux spectrum or power spectral density in the Southeast Pacific region. So wave numbers are on the horizontal axis and frequencies on the vertical axis. The length scales here span from the smallest 10 kilometers to the largest 1,000 kilometers. And in terms of time scales from roughly 2 hours to roughly 3 months, because we did averaging over a year of data. And the picture in the Agulhas retroflexion is very different. So this is the annual latent heat flux spectrum in the Agulhas region. Not only is total variance integrated over the domain much higher, and the ratio between the two regions is approximately 2.5, but we already kind of knew that from the standard deviation maps that I showed earlier. Really, what spectral analysis adds, the added value of this method, is that it tells us where in spectral space or at which time and length scales this variability or this variance is contained. And the eye can sort of make out that there are two regions or two regimes of elevated latent heat flux variability here. One is on the upper left at low wave number, high frequency, spanning from hundreds to 1,000 kilometers in scale approximately, and from hours to a few days. And the other is in the lower right, higher wave numbers, but lower frequencies spanning from tens to hundreds of kilometers and a few days to several weeks or a month or so. And there is a local maximum in the Southeast Pacific Chile region. It's weak, but it's there. And the idea was if the eye can see this, then we should be able to fit a spectral gap, so to speak, between or a partition line between these two regimes of elevated variance. And this is what we did. So we fit a partition line diagonally across the spectral space. And this was fit to remove any geographical bias. We fit this partition line on an average latent heat flux spectrum that was averaged across 6 regions disseminated through the Southern Ocean. And the regime above the partition line in the upper left is where, in terms of length scales and time scales, atmospheric pressure systems or synoptic systems and high frequencies live. And the regime below the partition line is where, in spectral space, ocean mesoscales and submesoscales live. And this right now is more based on intuition for physical time and length scales, but we verified on SST spectra on one hand and on wind kinetic energy spectra on the other hand that this partition made sense and that they were respectively below and above the diagonal overwhelmingly. So now integrating the variance in each regime tells us how much each regime contributes to total latent heat flux variance. In the Southeast Pacific, atmospheric variability dominates, representing 91% of total variance, and in the Agulhas retroflexion, oceanic variability dominates, representing 70% of total LHF variance. And so what we next did is that we extended this method to the entire Southern Ocean. So we repeated the spectral analysis every degree in longitude and latitude over the entire Southern Ocean, amounting to roughly 13,700 spectra. And in each spectra, we kept the percentage of variance in that region that was attributable to ocean mesoscales and submesoscales. And this is the map that we derived from this. This represents at each point how much latent heat flux variance is driven by ocean mesoscales and submesoscales. And so there are regions where latent heat flux variability is mostly ocean driven, such as around the Agulhas region, and other regions where it's mostly atmospheric driven, such as the Southeast Pacific around the Chile region. Now, putting this next to the annual mean eddy kinetic energy at the surface, we see a visual correspondence between these two maps. And visually, hotspots of mesoscale and submesoscale latent heat flux variability correspond to hotspots of eddy kinetic energy. And so if we scatter these plots one against the other, so the left against the right, this is the relationship that we get. And so there's relative mesoscale and submesoscale latent heat flux variance on the vertical axis and eddy kinetic energy on the horizontal axis, showing thus that there's a positive correlation between these two fields throughout the Southern Ocean. Now, if instead of scattering eddy kinetic energy against the percentage of latent heat flux below the partition line, we scatter it against the integrated or absolute value of that latent heat flux variance, we get the following relation in terms of absolute latent heat flux variance in the oceanic regime. And so what this tells us is that latent heat flux variance at ocean mesoscales and submesoscale can increase by an order of magnitude between low and high eddy kinetic energy regions. And one might ask, well, what happens to the variance above the partition line between the low and high eddy kinetic energy regions? And this one is much more, the atmospheric-driven latent heat flux variability is much more homogeneous across the domain. Now, there is a subtle increase that you may have noticed from low to high eddy kinetic energy regions. And this is still an open question as to why. A hypothesis is that the ocean might transfer more energy to the atmosphere in high eddy kinetic energy regions, but we haven't explored this hypothesis yet. And so this kind of wraps up the first question that we were asking in the beginning about the relative ocean and atmospheric contributions to latent heat flux variability, showing that in high eddy kinetic energy regions, the ocean mesoscale and submesoscale can drive up to 70 to 80% of latent heat flux variability. Now, moving on to the second question that we had about the atmospheric response to submesoscale SST fronts. So we're going to dive in or focus on high eddy kinetic energy regions that are populated with mesoscale eddies and submesoscale fronts. And for this, we're going to look at the Agulhas region as an example. So we would like to isolate the effect of ocean mesoscales and submesoscales on latent heat flux variability. And for this, we're going to perform a low-pass temporal filter. Why do we do this? If we look at the spectrum, the wave number frequency spectrum for latent heat fluxes in the Agulhas region, which is familiar to us by now, and we perform a 5-day low-pass filter on this field, what it does essentially is that it removes most of the atmospheric signal that was contained in the upper left of this spectrum. It does remove, granted, some of the higher wave number, higher frequency oceanic signal. However, we found that this low-pass filter was a simple method that was a good compromise to isolate the ocean-driven signal. And so to illustrate the effect of this low-pass filter, I'm going to show two animations real quick. So in these 4 panels, the upper left panel is the latent heat flux heat map that we already saw with winds and SST contours. The upper right panel is surface wind stress divergence. The lower right panel is downwind SST gradient. And the lower left panel is latent heat flux gradient amplitude. So this is an hourly animation of raw outputs of the simulation. And what this shows us is that focusing more particularly on the 3 panels to the right and to the bottom left. What this shows us is that atmospheric fronts and synoptic systems leave strong transient signatures on wind stress divergence in the upper right. You can see them coming through the domain with pretty strong signal. They also leave a signature in the latent heat flux gradient to the lower left. And to some extent, they modulate downwind SST gradient in the lower right. But after applying a 5-day low-pass filter, and this is now a daily animation, this is the picture that we get. And what we see here is that the oceanic signal or oceanic features that we had in the background in the first animation, here they really stand out. And the atmospheric signal that was overlaid in the first animations has been removed. And so looking more closely into these 3 fields, so wind stress divergence, downwind SST gradient, and latent heat flux gradient, there seems to be a visual correspondence between the features in these fields. And starting with wind stress divergence and downwind SST gradient, so the right panels, we looked at their joint distribution in the Agulhas region over a year. And this is the relationship that we obtained. So downwind SST gradient on the horizontal axis and wind stress divergence on the vertical axis. It's important to note here that downwind SST gradients, if you look at the scales, they span from roughly -5 to +5 degree per 10 kilometers. And these are very strong SST gradients, even after applying a 5-day rolling average or 5-day low pass filter. These correspond to submesoscale fronts on the order of 1 to 10 kilometers wide, roughly. And this joint distribution also shows us that wind stress divergence and downwind SST gradient are positively correlated, which is the intuition that we got from the animations, but this confirms it a little more quantitatively. And this correlation was revealed by Sheldon et al. In 2004 in satellite observations of SST and surface wind stress. However, the little white box in the middle represents the ranges of downwind SST gradient and wind stress divergence that were covered in the observations of this study. And really, the reason I point this out is to highlight the leap that is enabled by coupled models like COAS that enable us to investigate these small-scale coupled phenomena. Previous studies have shown that this positive correlation between downwind SST gradient and wind stress divergence are representative of a mechanism called downward momentum mixing, driving the near surface atmospheric response to some mesoscale SST anomalies. And this joint distribution shows that this downward momentum mixing is active down to some mesoscales. Now, coloring this distribution by the average or mean latent heat flux gradient now shows us that those submesoscale fronts trigger the strongest latent heat flux gradients. And this gives a, how would I say this illustrates what drives the near surface atmospheric response, or what the near surface atmospheric response is. But we're also interested in looking at what happens in 3 dimensions, in the vertical dimension. And so we are going to look into a case study that samples some of the more extreme gradients down here in terms of downwind SST gradient and wind stress divergence. So the case study is the following. In the Agulhas retroflexion region, we're going to look into a case study of northwesterly winds, so blowing from the northwest, off the edge of a warm mesoscale eddy, where upwind latent heat fluxes are intensified on the warm side, and they are suppressed or even slightly negative on the cold side. This triggers strong negative downwind SST gradient at the front on the edge of the eddy, co-located with a fairly strong wind stress convergence, consistent with the downward momentum mixing mechanism. Now, slicing vertically through this black transect here that's represented. First of all, these are the surface fields. So the wind blows from the left to the right, from warm to cold water. SST and latent heat flux drop at the front, and the front is 10 to 15 or 20 kilometers wide, and really you can pinpoint it by the downwind SST gradient and wind stress convergence that are very strong. And slicing in the atmosphere vertically above, this is the convective mass flux above the transect. And what this shows is that the surface wind stress convergence triggers upward vertical motions and convective mass flux right above the front. And it's important to note that this response really extends in the this atmospheric response really extends on the horizontal extent of the front. It's really co-located. So this convective updraft extends through the planetary boundary layer, represented by the dashed line here. It reaches mid-troposphere levels up to the signatures visible up to 3.5 kilometers height, and it's most intense right above the planetary boundary layer. This is consistent with previous studies in the Gulf Stream and the Kuroshio extension, showing a similar secondary vertical circulation above some mesoscale fronts. And it's important because it has the potential to export mass, moisture, and energy above the boundary layer to the free troposphere. So this wraps up the answer to our second question about the characteristics of the atmospheric response to some mesoscale SST fronts. And because it's such a small scale atmospheric response, it begs the question whether ERA5 captures these processes at all. So we're going to move on to the third and final question, where we compare CoAS with ERA5. ERA5 has 1/4 of a degree horizontal resolution, roughly 30 kilometers. Its outputs are hourly as well, and we extracted 10 years of the reanalysis. We're going to start with a big picture statistical, big statistical picture, I guess, that we started with. These are the maps that we already saw for CoAS. And I'm going to flip from left to right through the corresponding maps in ERA5. So starting with the left one, this was in CoAS, and this is the picture of the latent heat flux mean in ERA5. Spatially and in magnitude, they agree very well, within a few watt per meter squared from each other. So latent heat fluxes mean are very similar. Switching to the middle map now, this was the picture that we had in CoAS, and I'm going to flip to the middle map in ERA5. So overall, you might have noticed the picture is a little darker, signifying that there is a little more variability in ERA5, but this could be due to interannual variability since we have 10 years of data versus 1 in CoAS. But also the differences, if you look at the Agul and Chile regions, I'm going to flip back real quick. The differences between CoAS and ERA5 are well within typical reanalysis uncertainties in the region that were quantified by Swart et al. And finally, flipping to the last map on the right, this was SST gradient variability in CoAS, and I'm going to flip to ERA5. And so here the picture is very different. The SST gradient variability in ERA5 is on average 5 times weaker than in CoAS. So these results were a bit surprising to me at first because I couldn't quite wrap my head around how the surface boundary condition in terms of SST gradient could be 5 times less variable, and yet the latent heat flux variability be on par, so to speak, with CoAS. And I think this could be due to internal adjustments in the computation of the reanalysis. But overall, yeah, we haven't investigated this in detail. But so the next step was to look into spectral comparison or comparison of ERA5 and CoAS in spectral terms. And so these are the spectra for latent heat flux that we had in CoAS in our 2 example regions. And these are the corresponding spectra in ERA5. So the Nyquist wave number is smaller, but that's because the grid is coarser. Nothing surprising there. What is interesting to point out, however, is that total variance is comparable between ERA5 and CoAS, again, consistent with the standard deviation maps being comparable over the entire Southern Ocean. However, the relative contribution of the ocean mesoscale and submesoscale regime is underestimated in the Agulhas retroflexion. It dropped from 70% to 60%. And finally, fine-scale structures, roughly smaller than 80 kilometers, are attenuated in the ocean regime, but also in the atmospheric regime. And I'll get back to this in just a bit. Moving on to the joint distribution of wind stress divergence and downwind SST gradient. This is the picture that we had in CoAS showing positive correlation between the 2 fields and the latent heat flux, the submesoscale front generated latent heat flux gradients. And this is the picture in ERA5. So wind stress convergence and downwind SST gradient are also positively correlated in the ERA5 data. However, they cover much narrower ranges in ERA5 than they did in CoAS. And this highlights the absence of extreme gradients associated with submesoscale fronts in ERA5. And so this, the next step, final step you might expect is for us to look into a case study. And we are going to look into a similar case study to what we had in CoAS in the Agulhas retroflexion, a northwesterly wind event, where wind blows off the edge of a warm core mesoscale eddy. So at the front, a weakly negative downwind SST gradient is co-located with a weak wind stress convergence. And slicing vertically now through this black transect over the same distance as we did in CoAS, which was an 80-kilometer long transect, this is the response that we get in the atmosphere above. So convection is horizontally co-located here, not with the front, or with where the downwind SST gradient and wind stress convergence are strongest, but is co-located with the mesoscale horizontal extent. Vertically, it doesn't seem to extend that high, and it's more so intensified inside the boundary layer as it was instead of being intensified outside the boundary layer in COAS. So overall, the coupled submesoscale atmospheric response seems not to be captured in COAS. And this, I think, stresses the importance of resolving kilometer-scaled coupled processes in the ocean, of course, but also in the atmosphere. So this wraps up the third part of this presentation. And I'm going to summarize the key takeaways to end the presentation. So first of all, we showed that meso and submesoscales can contribute up to 70–80% of latent heat flux variability in high eddy kinetic energy regions of the Southern Ocean. And in contrast, the atmospheric-driven latent heat flux variability is much more homogeneous across the Southern Ocean. Second, we showed that some mesoscale SST fronts on the order of 1 to a couple of tens of kilometers wide can trigger a narrow convective response that extends beyond the boundary layer up to the mid-troposphere, with potential impacts on large-scale atmospheric circulation and water cycles. And finally, we illustrated that ERA5 does not capture this intense small-scale coupled atmospheric response, although long-term large-scale latent heat fluxes are comparable to what we saw in COAS. And there are two figures that I'd like you to walk away with. It's these two on the right. And as I said in the beginning, this work is in review with Journal of Climate, and the QR code will take you to the preprint. And with this, I thank you for your attention, and I'll take any questions.
Thank you so much, Lucie. Really interesting. Are there questions? I see Tony Lee has his hand up.
Thanks for the very nice talk. Lucie, I have two questions, but I'll ask one first, and the other people ask other question, and then I'll come back to my second question. The first question is, in terms of the frequency composition of the latent heat flux, not the spatial, have you looked at any comparison with mooring data to see whether COAS has a representative estimate of the high frequency and low frequency end of the latent heat flux?
Sure. So thanks. I mentioned these moorings in the beginning, so this is a great question.
Oh, sorry, I missed about first 3 minutes of the talk. Sorry.
So whether we looked into the frequency spectral content, or not even spectral, the frequency content, of the mooring signal versus the simulation signal. That's a great question. I did not integrate the signal down to just the. I did not look at the content in frequency terms. That would be something interesting to do. Qualitatively, we did compare just orders of magnitude of what the time series of a virtual mooring in the simulation would be against the real mooring data, but did not do a frequency analysis of that. That would be a good idea. Yeah.
Thank you. It will be a good vetting of the COAS model.
Well, Tony, do you want to go ahead and ask your second question, since I don't see other hands yet? I'm sure people are still thinking.
So the second question is, you assess ERA5 reanalysis. ERA5 reanalysis is a data assimilation, and it's not a model. It's not physically consistent, the different variables, because of data assimilation. But the operational analysis from ECMWF is physically consistent field that have the dynamics of ocean atmosphere coupling. So I wonder, if you look at that, whether there'll be less discrepancy.
No, we did not think to look at that. No, that's a good question. Did not think to look at that data set. Yeah.
Okay, thank you.
Lucie, can I ask, Just a technical question.
Yeah.
In COAS, how is the latent heat flux calculated?
Right. Yeah. So in COAS, the turbulent heat flux parameterization is an adapted version of the Helfand and Jaeger algorithm that was adapted to mid-range and high wind speeds. Yeah.
So are there, I guess the follow-on would be, are there things that you would think of improving based on what you've looked at, or things that should be scrutinized more in just in that representation of the turbulent heat fluxes?
That's a good question. I'll have to give that some more thought. I don't have a ready answer for you.
Something to ponder over a long time period. Yeah. Tudong has his hand up.
Yeah, I would like to follow Tony's question about the comparison between COAS and ERA5, which is fascinating. I got two things out of your comparison. The first one is the mesoscale the contribution from mesoscale, submesoscale eddies in the ocean to long-term latent heat means or variabilities is minimal. So correct me if I'm wrong. Question is, when you compare them, have you tried to downgrade the CoAS simulation to the same spatial resolution? Then make a comparison to see whether whatever the conclusion you have received still stand. My guess is it will, because the physics is in the model. Even you average them into quarter degree resolution, probably the feature is still there. But I'm just wondering whether you have any chance to confirm that.
Yeah, thank you. Yeah, that is yeah, I'd be curious to see what the result of that would be. I've not looked into that. I would be curious to see what that result of that is. Seeing that the physics that are modeled in COAS are modeled with different parameterization schemes than they are in COAS, than they are in ER5 in the ECMWF model. Yeah, I don't know. That's a great question. I'd have to think about it a bit and maybe just give it a try and see what the result is. Keeping in mind that, yeah, the parameterizations are scale dependent in COAS, and that I'm not sure what the result would be. That's a great question. Thank you.
Next is Johan.
Hi, Lucie.
Johan.
Great talk. It's really nice to see your work. I have a few questions or thoughts regarding scales, I guess. But the one thing I can ask you first is the ERA5 SST is known as the foundation temperature, which doesn't have the daily variance. What do you use in COAS in the model?
I'm sorry, you said the SST in ERA5 is the foundation temperature?
Exactly. So it doesn't have a diurnal signal, which can be 1 to 2 degrees, at least in the Agulhas region.
Yeah, so COAS, the COAS SST is, I'm not sure actually. I'm not sure how those two sea surface temperature fields compare in terms of the underlying models.
Okay.
Yeah, I don't know. I'll keep that in mind. And
No, I thought that could be a reason why you saw kind of a smaller gradient in the ERA5 field, because it's mostly mesoscale captured and doesn't get the daily signals. The second thing I thought was you spoke about the Nyquist frequency in your spectral plots. Could you just expand a little bit more on how you think that the native model resolution plays a role in how you can actually determine that is the small scale that has the effect, that you claim here on your last slide?
Yeah, so because the model grid is coarser, right, that automatically crops the wave number range, just mathematically. And so intuitively, from like right off the bat, the intuition is that smaller scales might not be as well resolved. But it's not just a clean cut at that Nyquist wave number. It also affects smaller wave numbers than just that Nyquist wave number. It rolls off much sooner than just that clean Nyquist wave number cut.
Okay, thanks.
Mome.
Hi, Lucie. My camera doesn't work, but yeah, I can still ask the question. Nice talk. I think, first a comment to the donor cycle question. I think Geos couples every 15 minutes, so you should have the donor cycle in there. Also, I think the difference in the boundary optimizations do not really matter there. My question is, so you try to make an argument about resolution against error 5, which is the data simulated product, and it's forced to preserve variance somehow with the real world, right? I think if you want to make the argument for resolution, you should compare to a free running coupled run of lower resolution. Right, so because so like find another model that doesn't do submesoscale, any CMAP model, basically use any CMAP model, and see what it does. You'd need high resolution output, but that argument would be straightforward. By error 5, you always get in these shenanigans with a simulated SST, blah, 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 right? They make the thing work so it looks good, but it's not a physically consistent thing at the boundary.
Yeah, for sure, for sure. The reanalysis has those internal nudges that make it physically not physically consistent. I think indeed it would be a good thing to look into a comparison with a coarser coupled model. The reason we chose to compare to error 5 is because it's considered gold standard in terms of reanalysis, and so it was interesting to us to see, like, okay, well, how does it capture some of it, part of it? What, like, does the response look different? But for sure, it would be good to compare it with a coarser coupled model that's physically consistent. Yeah.
Okay, thanks.
Next question is Rick Danielson. And we're not hearing you.
You're muted.
Yeah, you can type it.
Oh, you want to write it in the chat? Okay.
Well, Rick's doing that. Can I ask about the possibility, you looked at latent heat flux, which is a very reasonable thing to do. Have you thought about sensible heat flux? Is it the same?
Yeah, absolutely. Yeah, absolutely. We are actually running that right now. Looking at, so referring to this map in the top right, trying to, running the equivalent in terms of percentage of ocean-driven sensible heat flux variance. Yeah.
Cool.
Yeah. Can't see the chat. Sorry.
Okay. He says, Minobi 2010 captures a seasonal signal at larger scale. So to follow the potential impacts, one might ask if this has a seasonal impact.
So the question is whether there's a seasonal impact on the on which part, on the atmosphere, ocean relative contributions.
We'll have to get Rick to give us a thumbs up. second point, he says.
On the second point, on the submesoscale response, I don't know if there's a seasonal impact on that. What we did look into is as far as you can with a 1-year simulation, we looked into the seasonality of the meso of the ocean contribution versus atmospheric contribution, and found that there is seasonality, but not very strong. The second point, I did not look into the seasonality of the submesoscale triggered atmospheric response. Or the joint distributions, or in terms of joint distributions of the surface response fields. I don't know. Good question.
He says, seems ERA, previous version, could capture the larger scale impact, but this seems more interesting.
Yeah, I don't know. I haven't looked into that. Yeah, thanks for the question.
I think maybe a related question is there any prospect for getting COAS to run for long enough to have interannual variability in the simulation?
I hope, I wish. I wouldn't be the one to ask. I don't know. I don't know where that's at. Would be great.
Yeah, sounds like they're good questions that could be asked.
Tony has his hand up.
Tony has his hand up.
Right. So I heard that they are rerunning the COAS simulation now. Hopefully, it will be more than a year or more than the 18 months, whatever they have before. Also have a last question. The latent heat flux that you analyze are the flux from the model output, right? You did not compute from the state variable and isolate the impact of, okay, got it. Have you actually compute that from the state variable using, say, core algorithm and then compare with the latent heat flux output from model to see how they compare?
I did not do that. No, I did not do that.
It's all right. It's all right. Yeah. Thank you.
Yeah.
Okay. Well, if there are no further questions, I'll pause just a moment to see if anybody desperately raises their hand. But otherwise, thank you so much, Lucie, for a really great talk and great discussion. This was very stimulating, and it gives us lots of food for thought as we think about what happens next across the community.
Well, thank you. Thanks for the opportunity to present, and thanks for your attention.
Thanks, everyone.